Recall, the determinant of a 2 by 2 matrix A is given by matrix A, which first row is AB, second row is CD. That determinant is calculated by A times D minus B times C. For further learning objectives, we're going to need to look at IJ notation, where matrix A, instead of individually labeling parts A, B, C, D, we're going to label them by row and column using a subscript of numbers. The first number represents the row, that's the I notation. The second number represents the column. For example, this one, a subscript of 1, 1 means row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. The determinant is still calculated the same way. It's the A11 times A22 minus A12 times A21. So that part's not changing. It's just the notation, and it's the subscripts. Example, let A be the 2 by 2 matrix 3, -1, 4, 7. A11 would be this 3, row 1, column 1. 7, that would be row 2, column 2, etc. Your determinant is still calculated the same way. 3 times 7 minus -1 times 4. Those two negatives make a positive 4. 21 plus 4, that's 25. If you upgrade to a 3 by 3 matrix, the subscript notation represents the same thing. Like this one would be second row, third column, second row, third column. As far as calculating the determinant goes for a 3 by 3 is you don't have to start in the upper left, but it's usually a good idea to start there. We're going to take the value from first row, column 1. Now, if you were to cover up row 1 and column 1, ignoring the top row and first column, these 4 values down here are called a minor. The determinant of this 2 by 2 is what you're going to multiply this entry by. So take the value from row 1, column 1, put it here, and then pretend that these don't exist and concentrate on these 4 values. The determinant will follow and be multiplied. Then you change your sign in the next term, and if you go across the top row, you'll use a minus sign. Then take this value, minus sign, this value, and then if you forget about the top row and second column, your minor will be those two and those two. A21, A31. Again, cover up or ignore, finish out your matrix, and then you alternate your sign again, positive. So we went positive, negative, positive, and it's like a checkerboard of positives and negatives. But take this value, A row 1, column 3, put it down. Ignoring it, then you have these 4 values for your determinant. So let's do an example. Compute the determinant of matrix A that's given, row 1, column 1, so that A sub 1, 1 value is 1. Crossing those out, you have these 4 values left. Determinant of that 2 by 2 matrix, it's called a minor. Then alternate your sign to minus, so it's plus, minus, minus 5. Ignoring that top row and middle column, you're going to calculate the determinant of 2, 0 and -1, 0. And then alternate your sign again, plus 0. Ignoring top row, third column, then you calculate the determinant of those 4 values. Okay, so now we have we've got, for this determinant, it's 4 times 0 minus -1 times -2, and that's placed here. I tried not to skip many steps so you could follow in the notes. minus 5, and then the determinant will be 2 times 0 minus negative 1 times 0, and finally plus 0 times the determinant of this matrix is 2 times negative 2 minus 4 times 0. And if you make your calculations, your determinant comes out to negative 2. Again, feel free to check your work. The reason I'm showing you a lot of these extra steps is your homework on a few of them require you to show the steps instead of just a direct calculation. But if your problem asks for just a direct calculation, put it in your graphing calculator, let it rip. I did email you guys a few websites. Feel free to use any website that has a matrix calculator on it to help you out. Okay, so let's go down here. We're going to look at what's called a cofactor. We're going to call a cofactor, same notation, ij, I row, j column. It's defined as negative 1 to the power of the sum of the row and column times the determinant of the minor matrix the matrix with row I and row j swiped out, just like we did on the above example. But anyway, it's called the ij cofactor of matrix A. And so your determinant is going to be A11 cofactor of 1, 1, which is the sign and the determinant that we used up here. But anyway, if you follow this out and go across the top row, that's called a cofactor expansion across the first row of matrix A. As an example from the matrix above, the cofactor 1, 2 would be the cofactor of row 1, column 2. So it was the part that followed the 5, including the sign. So it's negative determinant of those 2 by 2. 1 plus 2 is 3. Negative 1 to the third power is negative 1. That explains the negative. And then the determinant of 1, 2, the minor, would be the 4 numbers left over after you ignore top row, second column. So it would be these 2 and those 2. And that cofactor has a value of 0. In a later video, we're going to come back to cofactor and use it to find inverse of a 3 by 3. Properties of determinants. Let A be a square matrix. If a multiple of one row of A is added to another row to produce a matrix B, then those two determinants are equal. Row operation of multiplying one row by a value and adding it to another row does not change the determinant. If two rows of a matrix are interchanged, then the determinants will differ by a sign. If one row of A is multiplied by some constant, then the determinant will be also multiplied by that same constant. Example, let's let A be this 3 by 3 matrix. We're going to compute its determinant. All right, now for this particular learning objective, the strategy is to row reduce your matrix to get it into triangular form. It doesn't have to be row reduced echelon form, just row reduced, echelon form. And I'll go over that when we get to the bottom of the example. Once you can get one in triangular form, if you can, the determinant's the product of the diagonals. So that's kind of handy. Okay, so let's take matrix A. I'm going to take 2 times row 1 plus row 2 and put the answer in row 2. I'm going to recopy row 1 and row 3 because I'm not doing anything to those two rows yet. 2 times 1 plus negative 2 is 0. 2 times negative 4 plus 8, that's also 0. 2 times 2 plus negative 9, that's negative 5. I'm going to swap rows 2 and 3, nothing more. And then finally I want to create a 0 here so that I have triangular form. I can make 0 here by just simply adding row 1 and add to 2. row 1 plus row 2, putting the answer in row 2. 1 plus negative 1 is 0. Negative 4 plus 7 is 3. 2 plus 0 is 2. And then now I've got it in triangular form. Once you get it there, it's the product of your main diagonal. 1 times 3 times negative 5. Be very careful here. If you go back to the top, this part covers number 1. Multiplying a row and adding it to another, the determinant stays the same. So that doesn't affect the determinant. It's here where the rows have been swapped. If 2 rows are interchanged, then you're going to have to negate, and I made a note here, this step here where you swap your rows requires a sign change. So that's an extra negative multiplied into your diagonal product. And so it actually makes the determinant positive 15. We didn't have to multiply any row, but suppose we took a row and multiplied them all by 1/5, then you would also take 1/5 times your diagonal product. Note the first and third operation here and here don't affect your determinant. It doesn't change any values. It's that swapping to get in triangular form, that's where it made the difference. Theorems. If matrix A is invertible, a square matrix A is invertible if and only if its determinant is not 0. If A is a square matrix, the determinant of A is equal to the determinant of its transpose. If A and B are square matrices, then the determinant of A times B is equal to the determinant of A times the determinant of B. Example, let matrix A be a 2 by 2, B is also a 2 by 2. Determinant of A, 6 times 2 minus 1 times 3, 12 minus 3 is 9. If you were to use your calculator to do the inverse, you would get decimals in here, but remember you could hit math and enter twice to change them all to fractions. But as a courtesy, let's remember the inverse is 1 over the determinant, so it's 1/9. Swap your main diagonal, so 6 and 2 change places, and the other diagonal you negate, change their signs. The transpose of A, column 1 becomes row 1, column 2 becomes row 2. The determinant of this transpose is 12 minus 3, which is also 9. And that's just back up here at number 2, where the determinant of a matrix and the determinant of its transpose are equal. Number 3, A times B, if you multiply these two matrices, you get a 2 by 2 matrix that has these 4 values. We've calculated the determinant of A already, that's 9. Determinant of B is 8 minus 3, which is 5. 9 times 5 is equal to 25 times 13 minus 20 times 14. Yeah, I have to have a calculator to do that one. That diagonal minus that diagonal gives you 45, which is the same as determinant A times determinant B. So I bundled all 3 of those theorems up in one. Each one is a numbered example of each theorem. Definition for an n by n matrix A and any vector in Rn, let A sub I B of B be the matrix obtained from A by replacing column I by the vector B. And so this is tricky notation, and it's more clear when we do the example at the bottom. But by definition, A sub I, you would go all the way over to your ith column, and then that would get replaced with whatever vector B was given to you. And so that leads us up to Cramer's rule, and that's a theorem. Let A be an invertible n by n matrix for any vector b in Rn. The unique solution of x for your matrix equation Ax equals b has entries given by x sub I, where I represents natural numbers, and it'll depend on the size of your matrix too. However big your matrix is how many of these I increments you go. But it's the determinant of matrix A with a column swap progressively divided by the overall determinant of the original A. So as an example, let's take this two equations, two unknowns. Matrix B, vector B is out here. It's that 6, 8 column vector. So matrix A is the coefficient matrix of x1 and x2. So we're going to take these four numbers, 3, -5, -2, 4. That's matrix A. Okay, now A sub 1 of vector B is you take the first column, but you replace it with this vector. So this actually goes into column 1. Column 2 stays the same. And that's your matrix A sub 1b. Matrix A sub 2b is, you guessed it, you're going to take the second column and replace it with vector B. So you'll maintain 3, -5, but the second column gets replaced with 6, 8. It's just that simple, but that you got to keep a watch on it too. The subscript is the column that B is replacing. So if it's a 1, column 1 gets replaced by B. If it's a 2, column 2 gets replaced by B. Okay, now since this is two unknowns, your solution vector X, the first one, and we're going to go here, x sub 1, it's the first entry of the solution. It's the determinant of A sub 1b. A sub 1b, its determinant is 24 minus -16, which is 40, over determinant of the original coefficient matrix A, which is 12 minus 10, that's 2. 40 over 2 is 20. All right, so that's the top entry of our solution. And remember, x is what we're looking for. That's the solution. X sub 2 will be the determinant of A sub 2, where the second column is replaced with B, over the determinant of the original. Determinant of A sub 2b over the determinant of the original, which that's going to still be 2. Column 2 replaced with B gives us a determinant of 24 minus -30. 24 plus 30 is 54. Divided by 2 is 27. So each I in a column vector represents your solution. Had this been 3 equations with 3 unknowns, we would have to do 3 column swaps. We'd have A1, A2, A3, where each column was repetitively swapped by your exterior numbers. And then your answer would have 3 entries instead of 2.